So, hi everyone, let's start today's session. Let me share my screen first. So, hi everyone. Am I audible and is my screen visible? Please confirm. I think there is one student here. Rohan, can you confirm? Okay, great. Thanks. Fine. So, yeah. So, let me cover up the remaining problems from the previous sessions and then we can start this session. Yeah, so let's start with some basic problems, some simpler problems, and then we'll start with the topics for today's session. So the problem says, prove that a determinant of a upper or a lower triangular matrix is equals to the product of its diagonal elements, right? So I think other students are also joining. Yeah. So let's start with the proof. So let's say we have this kind of matrix. So let's consider the 2 by 2 case first, right? So let's say we have a 2 by 2 matrix and we want to prove that the diagonal, the determinant is equals to product of diagonal elements, right? That's a very simple proof. So let's say we are dealing with upper triangular matrices, and so I will prove for upper triangular, similar will follow for the lower triangular matrices. Upper triangular matrices, right? So let's say the matrix has entries A, B, C, and this is 0. So this is a 2 by 2 upper triangular matrix. Now we all know the formula for upper triangular formula for determinant. So determinant is equals to A into B minus A into 0. So which is equals to A into B. And now since this is equals to product of the diagonal elements. Now this I have proven I have proven for the base case, which is R2 cross 2, right? So let's start with uh, now how can we proceed? You can let's start with the 3 by 3 case, and then we will see a pattern, and from there we can prove. Let's say we have a 3 by 3 matrix, then ABC 0 DE 0 0 F, right? Now again we want to find the determinant of this upper triangular matrix. Determinant is equals to A into the determinant of minor matrix of A, right? So A into determinant of the minor matrix of A, and the minor matrix of A is this matrix, right? Everyone, I hope you are familiar with this, right? So now this is equals to A into D into F minus E into 0, right? Minus minus B into, now again, minus B into determinant of the minor of B. So do you know the minor matrix of B, which is essentially a matrix containing these two columns, right? Matrix containing these two columns. So the determinant is F into 0 minus E into 0, right? Plus C into, so again you choose C here, and you take the determinant of this minor matrix, which is essentially C into 0 into 0 minus D into 0, which is equals to A into D into F. Again, A, D, F are diagonal elements, right? These are the diagonal elements, which is equals to, sorry, which is equals to product of diagonal elements of the matrix. Fine. Now let's say we talk about some. So for this is we have done for 2D and 3D cases. We can do this for general cases also. So let's say if we have a matrix M cross M, and you should know that determinant is only defined for square matrices. So this has to be M cross M matrix, right? And yeah. So now let the matrix, how it would look like. It would look like uh, A1, A2, dot, 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 AM, 0, AM plus 1. So let's not do this. Let's make it index notation. So let's say this is A11, A12, dot, 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 AM, 1M, right? Then 0, A22, dot, 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 A2M. And then this is basically a low upper triangular matrix, right? So these all entries have to be 0. So this is a big 0, right? All the entries are 0. And here you will get up to AM, M, right? So this is some sort of upper triangular matrix. Now again, how to find the determinant? This is a generalization of upper triangular matrix for general case, which is M cross M, right? Now how to find the determinant of this matrix? Again, determinant is equals to A11 into determinant of minor of A11, right? So minor matrix for the element A11, right? So the minor would be this matrix, right? This is again an upper triangular matrix. Fine. So now what is the determinant of, so let's write up the minor of A11. So minor A11 will become, I think this is called the minor matrix, yeah. So this will become an M minus 1 cross M minus 1 matrix that will look like A22 dot 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 A2M. And again, this is a square matrix. Fine. This is a square matrix like this. And the lower triangular part, the elements below the diagonal will be 0. So the elements below the diagonal will be 0. So you will see A3M here, and towards the end, right, A3M and AMM, right? Am I right? Yeah, I am right. Yeah. So now again, this is a lower upper triangular matrix, right? So you keep doing this, keep finding the minor, and eventually you will see that you will reach to a 3 by 3 case. So keep doing this, and in the end you will reach a state of a 3 by 3 matrix that will look like basically. So this was AMM, right? This was A M minus 1M. This would be A M minus 2M. So what I'm doing, I'm saying is, I'm just trying to find the determinant of minor of A11. Sorry. So this is not exact determinant. I'm trying to find the components required for finding the determinant of this matrix. The component are the determinant of minor of A11, determinant of minor of A12, determinant of minor of A1M. So this is a minor over here, right? So minor. Yeah, right. Fine. So now I'm only dealing with minor of A11, and we will repeat this for all other top row elements also, right? So now you repeat this process, and let me add a page here. Yeah, that's good. Yeah, so we are here. Fine. So now so we were dealing with minor of uh, A11. So now when you keep repeating this, right? So basically I was trying to find the determinant of minor of A11 so that I can figure out that component of determinant related to minor of A11. Right now, again, you get some matrix of dimension m minus 1 cross m minus 1. Right now, what you can do, you can simply again choose in this matrix, you want to find the determinant of this matrix. So again, you will get this lower triangular matrix. So this which is here. Let's copy this here and paste this here, right? So this will be the minor of A11. Now again, the determinant of this matrix is essentially the determinant of minor of A22, right? So again, minor of A22, you will see that will be an upper triangular matrix. And eventually, if you keep repeating this, you will see that you will need to find the determinant of a 3 by 3 matrix, right? Determinant of a 3 by 3 matrix. I think I wrote that matrix. Right. This is here. No, this is it. Okay, fine. So you eventually will need to find the determinant of E3 by 3 matrix that looks like AMM, AM minus 1M, sorry, AM minus 1M, AM minus 2M, right? So this is AM minus 2, uh, M minus 2, AM minus 2, M minus 1, right? And this is AM minus 1, M minus 1, and this will be 0, 0, 0. Now you know the determinant of this matrix is essentially the product of the diagonal elements. So you will get AM minus A, sorry, AM minus 2, M minus 2 into AM minus 1, M minus 1 into AM, M, right? So determinant of this minor matrix for some submatrix is this one, right? Now let's go back up. Now retrace the path to get the determinant of the final matrix. Now what you have to do, you have to multiply this thing with the matrix element that is along the diagonal. That is, so basically the determinant, the component from here will be this component, right? So let's call it let's call this matrix as minor last. So this is the last minor matrix. So basically this determinant will be multiplied with determinant of minor last, right? Multiply it with AM minus 3, M minus 3, right? Right. And then you will see that this will be multiplied by AM minus 2, minus 2, M minus 1, M minus 1. So this will eventually go up to A11. So this component will essentially become product of I AII, right? I will go from 1 to M, right? So this will be the component from the first element of the row 1, which is A11. Now, so we have some part of the determinant, right? So this is something. So the determinant of total matrix, determinant of matrix M will be equals to this part, I equals to 1 to M into A1II plus something, right? Now, what is that something? Let's figure out that. So that something is essentially the determinant of minor of this, determinant of minor of this, and falan up to this, right? So one thing to observe here is I'm just going to show this for A12, and then you can do the rest for that. So how does the minor of A12 looks like? Minor of A12, right? It will essentially look like a matrix formed by removing these and these row and columns. So what you will get, so I'm removing this row and this column. So you will get 0, any something, then 0. So you will get this row minus this. Then again this row minus this. Okay. Huh. So minor of this A12 will be essentially looking like some matrix with zeros across the diagonal, right? And some non-zero entries on the upper side and zero entries on the non-zero entry here and zero side zero entry here, right? So now again, this is minor of A12 that you can see just by removing the rows and columns. And now what is the determinant of a matrix with diagonals filled with zero? In fact, a upper triangular matrix, right? Matrix with all elements at diagonal and below diagonal. So what is the determinant? You will get that determinant will be 0. Why? Again, you have to do this again. So a very simple process. Like the way we were trying to find the minor of A11, determinant of minor of A1, and we reached here, right? Now let's say A11 was 0. And all the entries A11, A12, A11, A22, A23 up to AMM are 0, which is basically this matrix. What you will get, the determinant to be product of all the diagonal elements, right? This we have already seen this, right? So if any one of the diagonal element is 0, the determinant will be 0. And since all the diagonal elements are 0, you will get some sort of 0. Even, yeah, right. There might be a case that some diagonal elements are not 0, but let me see. We will get the first diagonal element itself is 0, so you will get a 0 entry, right? So the determinant will be 0 for this, and eventually, again, you can see this for any general entry of the first row. Like for all these entries, the determinant of minor will be 0. So eventually, the something will become 0. So something will be 0. Hence, determinant of M is essentially product of I equals to 1 to M. AII, which is equals to product of all diagonal elements. Fine, everyone. Is there any doubt in this? Everyone, do you have any doubts in this? If you have any doubts, please type in the chat box. Anyone, do you have any doubts?
My
Yeah.
doubt is when you do that factorization L and
L and U, what? Yeah.
U for a given matrix A, will L and U be unique? That was the question in
For the
the
LU
assignment.
decomposition.
Yeah. That was the question in the assignment in week 7 assignment. L and U, are they unique?
So this was a question in the assignment problem, or
Yeah,
this?
assignment week
I mean
7.
NPTEL's problem statement, right?
I answered the 10 questions, only one was correct. I got 1 mark. But this class was not done at that time. That is 10th September was the last date. Today
Okay.
is 12th, no?
Yeah, right.
So I answered it as unique. Is it correct?
I mean, did the
L and
answer?
U, L and U will be same for a given matrix, or can they be different?
Um, have you been taught about this?
Actually,
I mean,
yesterday night only first lecture 36 I attended. That was by
okay.
Arun Lal, and it was on vector spaces.
Hmm.
But this, I think, is already covered in the previous what is that, week 6 or something. I
Hmm.
mean, week 7.
Okay.
And week 7 assignment deadline was 11th September, no, 10th September 2025.
Hmm.
10 questions I answered. That least square, sum of least square, all those things. But I couldn't answer those things. But the first
Hmm.
question was this, it has given correct. 1 mark it has given.
No, but the thing is, I cannot answer those questions, right? Because they are
Oh,
assignments
I
for
see.
this,
Oh, okay, okay.
right?
Sorry for asking. Sorry.
Because I can't answer this because these are the problems. These are graded assignments, right?
Yeah, to be submitted. Yeah. Yeah, deadline is over
Ah,
now. Deadline is over now.
okay, okay, fine, fine. Then yeah, you can. Then it's fine.
So
Okay.
LNU can be unique or they can be different also.
Acha, so they can be different also, right? Because LU decomposition is not exactly unique. You can find different, basically find different ways to write in lower and upper triangular forms. So they are not
Okay.
unique actually.
Okay. Thank you.
Yeah.
Thank you.
So yeah, let's resume. So anyone, do you have any doubt in this proof? Okay, fine. I think there is no doubts. Is my screen visible? Okay, I'm just resuming the podcast. Yeah. So this was one of the questions from the second last problem week, right? So the next question is, so this is from week 7, right? This is from week 7. Okay. Fine. So let's move on to the next question. Some okay. Prove that determinant of A inverse equals to 1 by determinant A for a square matrix, right? A for a square matrix. Now again, why square matrix? Because determinants are only defined for square matrices. So let's see how to do this. So yeah, um, fine. So do we know the relation between A and A inverse? Everyone do. I hope you are familiar with the idea of multiple matrix inverse. That is basically gives you the identity matrix. So when you multiply a matrix with its inverse matrix, the square for a square matrix with its inverse, you will get the identity matrix, right? Uh, Fine. So how to show that this is equals to identity matrix? So basically, this is the property of the inverse, right? So let's say A is a M cross N matrix, then sorry, M cross M, right? M cross M. Then you will have some A inverse that is M cross M. A cross A inverse is equals to identity, where I is a M cross M identity matrix, right? So now let's prove that determinant of A inverse equals to 1 by determinant of A. So we all know one property of determinant, that determinant of A into B is equals to determinant of A into determinant of B. Fine. So now let's use this property and put it here. You will get that determinant of A into A inverse is equals to determinant of A into determinant of A inverse, right? Now on the RHS, you have the, so now it is given that A into A inverse equals to identity. So determinant of A into A inverse equals to determinant of identity, right? Now the identity matrix, the determinant is 1 for identity matrix. Then you can say that determinant of A into determinant of A inverse is equals to A inverse is equals to 1. This gives you the proof that determinant of A is equals to 1 by determinant of A inverse. So this is proved. Hence, fine. A very simple application of properties of determinant. Fine. Anyone, do you have any doubts? I think no one has any doubts. So let's proceed to the next question. So let's say if A equals to this, so we have A matrix and U matrix. So then it is given that A equals to LU, then the what will be the lower triangular matrix, right? Everyone, do you need to me to solve this problem?
Yes, please.
Okay, fine. So let's say A is equals to LU, right? And U is given. So what should be the lower triangular part? Fine. And yeah, okay, fine. So let's proceed. So if you know this, you can say that A into, since U is invertible, this U matrix is invertible, you can say A inverse equals to L, right? Now, what you have to do, simply solve this equation, solve this matrix inversion and problem. So U inverse is basically 1 by determinant of A U into uh, cofactor of U transpose, right? So let's do this. Determinant of U is essentially 2 into 3 into 1 by 3. So it's a diagonal matrix, right? So 2 into 3 into 1 by 3, which is equals to 2, right? Now let's figure out the cofactor matrix. So it is essentially cofactor of U is essentially the just start taking the determinant of the minors, right? So minor, oh sorry. So minor of 2 is uh 3 into 1 by 3, which is 1, right? And then, yeah, it's a diagonal matrix, so you don't need to take care of about this. Then again, for 2, it will be 0. For 4, it will be again 0. Then for 0, it will be 2 by 3. And then, so, and this will be minus 2 by 3. And then for 3, it will be 2 by 3 plus 2 by 3, right? And for this again, minus 0 to 0, right? Now for the last part, yeah, last row, for the 0, you will get 2 into minus 1, minus 7 of 12. So basically minus 14, minus 14. And then this is so plus minus plus minus plus, right? So this is 0. So for 0, you get minus 2 and minus minus plus 2 here. And then finally, for the last part, you get 3 into 2, 6. Now what you have to do, you have to just take the transpose. You get 1 minus 2 by 3 minus 14. 0, 2 by 3, 2. And wait a minute. So what is the, so do we have to take the inverse transpose? Okay, it's not transpose here, right? Yeah, because, oh, this is right. Because we should get and lower triangular matrix, right? Okay, this will be upper triangle. Yeah, this has to be transpose, right? So this becomes 1 minus 2 by 3 minus 14, 0, 2 by 3, 2, 0, 0, 6, right? And just divided by, right. So just divided by the determinant, right? So everything becomes 1 by 2 times this. So this is U inverse. Now what you have to do, you have to multiply A into U inverse. A into U inverse is essentially 1 by 2 into the product of these two matrices. So let me write down the matrix. 2, 2, 4, minus 1, 2, minus 3, 1, 2, 2, right? And then U inverse is basically 1 minus 2 by 3 minus 14, 0, 0, 0, 2, 6, and then plus 2 by 3, right? Minus 2 by 3 minus 14 and plus 2 by 3. Just do the matrix product and you will get the answer. Fine. So it will become 1 by 2 into this, which is essentially 2, this into this, which is essentially minus 4 by 3 plus 4 by 3, 0. This into this, which is minus 28 plus 4 plus 6 over 24. So 24 plus 4, 24, 28, 0. Now again, you get minus 1, minus 1, minus 1 plus 1, minus 1. This will be 0, but let's finish it. That should be 0. So plus 4 by 3. Okay, yeah, this need not be 3, yeah, right. Plus 4 by 3 plus 2 to the 4 by 3, right? Plus 2 by 3 plus 4 by 3, 6 by 3, 2. And then the last one will be 14 plus 4 minus 18, which is 0, right? And then 1 here, and then minus 2 by 3 plus 4 by 3. And this is 2 by 3 here, right? And then this minus 14 plus 4 plus 12. 12, sorry. Okay. Yeah. So this will become 2, right? So this is essentially a lower triangular matrix that looks like this: minus 1 by 2, 1, 0, 1 by 2, 1 by 3, 1. This is the answer, right, everyone?
Thank you, sir. Thank you.
Yeah, Rohan, what's the doubt you have? Rohan, you are unmuted. What is the doubt? Yeah, I think your mic is not working. You are muted right now. You are muted. So what's the doubt? Can you just ask it?
Yes, sir. Sir, now am I audible?
Yeah, yeah.
Sir, this method is nice actually. I didn't think about taking U inverse, but
Yeah.
so I was doing row reduction basically, like how we
Okay.
derive
Huh.
LU from A.
Hmm.
But what if there is a zero element in the diagonal and we can't
Hmm.
take U inverse in that case? Then do you have any other method? Or like then you will also go to that.
So if you have that kind of situation, then again, if you are doing, so let's say you are doing RREF on A, right? Trying to get the lower triangular and upper triangular part separated out, but then your pivot element will be 0, right?
Mhm. Right. So,
Fine.
but in
So
that case, LU decomposition will be possible, right? So there might be
it
one
won't
case.
be it. Yeah.
So yeah, so I'm asking that LDU is not possible for a particular case, but LU is possible, right? In that case.
LU is not possible. So if there are some sort of situations where your diagonal element are getting 0, you might need to pivot it. So like basically pivot the PA is equals to LU is always possible. But which is P is a permutation matrix where you are swapping the rows. But LU itself is not always possible.
Okay, so I might be able to better understand you if I give you the example what I'm thinking.
Yeah.
Let
Yeah.
me make a let me make it reverse wise. So I have two matrices. LU I'm considering, not A. So two
Yeah.
matrices I'm telling you. One is
Hmm.
2 by 2, two matrices. So let me
Hmm.
make the first one as uh, 1501.
1 is diagonal, right?
Yeah, 1501. It is a 2 by 2 matrix. So I'm taking it a small example.
Acha.
Yeah. Uh, okay. The reverse thing actually. So 1051. Okay. My bad. Yeah. No, sir. In LU, so L is lower triangular, right? So I was saying 1051, row wise 10, and then 51 in the second row.
So the first matrix is right?
No, it is an upper triangular matrix. I'm saying that make it a lower triangular matrix. So 10 in the first row, and in the second row
Okay.
51.
Okay, fine.
Yeah. So the right hand side, the matrix that you have written, it is my L, and write U as 1200. Not that U. Can you write a new U? Yeah. 1200.
What? Hmm.
1200. Yeah.
Hmm.
Right. So it is a lower triangular matrix and an upper triangular matrix. Am I right on this?
This is right. Basically, no entry has to be 0 below the diagonal. All the elements below 0 has to be at
Right.
0 element, right?
So if I multiply it, I will get a matrix. So I can call that
So
matrix A.
it will be a singular matrix, right? It will be
Yeah. Right.
it won't be a full rank, right?
Right. Because U is singular.
Yeah.
Yeah. So for this matrix A, we still have LU decomposition, right? What will be that matrix? 1, 2, and 5, 10,
Five.
I guess. No?
Wait.
5, 10.
5 2s are 10, right? Yeah,
Right.
5 10.
So for this matrix
Now,
also we have LU decomposition.
will you be able to get that, right? So let's do this. Um, can we find this? So let's do this. So you apply row reduction and you get this minus this. So you get 0 0 1 2, right? So now this is an upper triangular matrix and the lower triangular matrix will look like, right, 1 0. Uh, uh, this will look like, yeah, inverse of this. So the inverse of this will be inverse of 5. You're doing 5 into row 1 plus minus, yeah, right, 5 into R1 minus R2. This is your R2, right? So yeah, this decomposition is possible. Yeah, this is possible, but yeah, this is not useful, right?
Okay. So actually, what I was asking is, suppose the
Hmm.
given matrix U, it has a
Hmm.
diagonal entry as 0. It can have,
Hmm.
right? Theoretically,
Hmm.
it can have a diagonal entry as 0. So in that case, I won't be able to use the U inverse thing.
Yeah, right. But in
Like,
that case, you can always you need A, right? So what is the A here? A is here, right? So 1 2 5 10, and you want to go from here to, let's say, 1051 into 1200, right? You are saying,
right,
can we reconstruct this L from here, right?
right.
Okay, so let's do this. So again, you are applying this operation. So what is that you are doing here? What it's, so 1 2 5 10, and then you are doing so the first row is same, right?
But
The
R2 should be
second
R2
row,
minus 5 R1, no? Or you have written
uh
the inverse operation there.
yeah, whatever you write, it's fine.
Okay, okay.
Any order, it's fine. So let's say you are writing minus 5 here and 1 here, right?
Right.
Fine, is this correct? Now
Yeah, yeah.
take the inverse
Yeah.
of this matrix. So this is L inverse, and you get the matrix 1 2 0 0. Now you take the L inverse of this matrix and you will get the answer. So L inverse would be basically determinant, which is 1. So basically it becomes these are, this is the inverse, L inverse. So this is with the L matrix. Yeah, you can get from here to here.
Okay, okay,
Is
right.
this fine?
So, yeah, yes, sir, yes, sir. Actually, I didn't think about this inverse taking thing. It will be easier
Yeah.
actually if we don't have diagonal entries as 0. Taking inverse will be
Hmm.
faster, I think.
Yeah, it will. No, basically taking the inverse is faster or not. It is essentially dependent on the algorithm that you're using to find the inverses. But for, let's say, 2 by 2 or 3 by 3 matrices, we know the analytical equation. So because that's why we the result is very quick. But
Okay.
when you go into the application of these algorithms on computers where they have coded up these algorithms, then in writing this algorithm, yeah. So in writing those algorithms, you will need to take care of whether to use the inverse way or the reduction form, whatever. So it is completely dependent upon the problem there. So for now, you can assume that, yeah, inverse is quite intuitive if the matrix is invertible. If it's not invertible, you can do this process.
Okay.
Fine.
So, sir, is it safe to say that LU decomposition exists for every matrix?
No, it does not
Oh, sir.
exist
Okay,
for
okay.
matrix.
Apart from that pivoting
PALU,
part, yeah. So apart from that
PA is
pivoting
equals to
part, will it always exist, or like pivoting is the only problem that we can encounter, or there might be some other
Yeah,
problems as well?
you can do the pivoting and you will get the solution.
Okay, 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 sir. Yeah. Thank you.
Anyone else? Do you have any doubt? Shiv Kumar is raising their hand. Can you type? Yeah. Yeah, Shiv Kumar, can you ask your doubt?
example, what Rohan Biswas gave, matrix U is not invertible.
Okay.
Will it apply here? When you say A is
Uh,
equal to LU,
yeah.
U must be invertible.
Basically, what is the statement? The statement says, can you write a matrix A as a product of a lower triangular and an upper triangular matrices, right? So if you
Correct.
see this case, yeah, you are able to write it like this. It's only basically a naming convention, like what is the definition of upper triangular and lower triangular, right?
So in
So
that
for that,
case,
so basically, you can write this LU for this matrix. Now, U will be singular if A is singular, right? So if the matrix A is singular and you are writing A as a product of two different matrices, then there has to be at least one matrix which will be singular, because the rank of A is not full.
three.
A is not a full rank, right? Not full
Okay.
rank. So again, either one of these two has to be not full rank. So at least one. And the case we saw in this, U was not full rank.
Oh.
Right?
So if A
Now
is
the LU
non-singular,
decomposition, yeah, LU decomposition only says that can you write it as a product of LU, uh, basically can you write it as LU part? And I think there is some hard restriction on the definition of lower and upper triangular matrices. Basically, the diagonal element cannot be zero. So if you consider that case, then yeah, for a singular matrix, LU decomposition does not exist. If you say that L lower and upper triangular matrices cannot be have non-zero diagonals, cannot have zero diagonals, right?
so there are
Then
restrictions on that. Diagonal
Yeah, yeah.
element must be non-zero.
If yeah, that's a restriction. If there is that kind of restriction, then you don't have a LU decomposition for a singular matrix, right?
Okay. Thank you, sir.
sir, actually, that hard restriction, the diagonal elements cannot be zero. I think it
Yeah.
is not there. Otherwise, that particular LDU decomposition wouldn't be there in the first place. So
Yeah.
LDU decomposition exists if that diagonal elements are non-zero. And for the other things, when diagonal element
Hmm.
can be zero, and if pivoting is not an issue there, then we
Hmm.
can have LU. Quite
Yeah, yeah.
standard.
So basically, I'm just saying it is all up to the nomenclature, is the
Yeah, yeah, right,
convention
right.
that you are choosing. So let's say you are writing LDU and you are defining diagonal matrix with non-zero diagonals, right? So this is again a constraint, but it can have zero diagonals. So the
Okay,
only definition, the only thing that definition says that all the elements before below the diagonal has to be zero. There is no other extra content in that. So in
okay.
that case, it can have.
No, sir. I think in that case also it cannot have, because in LDU decomposition, the restriction is
Hmm.
not on these diagonal elements, but the restriction
Hmm.
is on use diagonal elements. They should be one. So when you
Uh,
have use
like
diagonal elements as one,
Yeah, right. So any decomposition you talk about, let's say I am talking about LU decomposition, I am giving a theorem on
hmm,
LU decomposition, right? Factorization. So I will state the properties that the matrix L should contain, the properties that U should contain. Now, let's say for our case, we are saying L is a lower triangular matrix that only says that the diagonal above the diagonal has to be zero, and similar and the opposite for upper triangular matrix, right? So that are the constraints provided before specifying the decomposition. If those constraints are satisfied, whatever matrix you write, it's correct. So now for LDU decomposition, there are some constraints. And if those constraints are satisfied, then it is fine. It's not about the name, it's about the properties that that name carries. That is only what I'm saying.
yes, sir, right. Yeah,
Right? So
got
you can define whatever constraint you want and give a convention to it. But if we consider the convention that upper triangular matrix have non-zero elements above the diagonal, this is also a definition. But the only definition that we know is that the elements below the diagonal have to be zero. Fine. So that does not say anything about the diagonal elements or the elements above the diagonal. For example, a matrix like this, let's say I'm writing 1, 1, 0, 1, 2, 1, 1, right? So, and here 0, 0, 0, 0, 0, 0, right? This is also, okay, yeah, let me correct this also. This is also an upper triangular matrix since all the entries below the diagonal are 0, right? So this upper and an element in the upper triangular part is also 0, but that does not violate the condition. That does not violate the constraint. So it's everything up to what your constraint you are defining. If those constraints are true, then this theorem is true and the results are true. That's it. So don't
Right.
learn anything. Don't just try to learn that if LU exists for everything and does not, try to see when it exists. Just go to the definition and try to figure out if it actually exists. Like for this case, you can say that this is an upper triangular, it is a lower triangular. Don't just learn that no, LU cannot exist for singular or non-singular. Fine.
Right.
Just
Yes, sir.
go behind the definition and see what are the properties of that should be satisfied for this.
Okay,
Fine.
sir.
Anyone else? Do you have any doubts? Fine. So this is the next question. The least square. Yeah, the thing that we did not cover in the previous session was the least squares problem, right? So the least square solution to the systems of equations this is. So now with this, let me cover the least square part also. Fine. Now let's say I have this XY plane, right? And in the XY plane, I have and I have some set of equations. So let's say I have three equations. AX plus BY is equals to 0. A1X plus B1Y. A2. So let me take concrete examples, right? So let's say X, one equation is X plus Y equals to 0. Second equation says X plus Y equals to X plus 2Y equals to 3. And let's say the third equation says 2X plus 3Y equals to 3. Let's try to solve these equations, these systems of equations, right? So everyone, can you give me an idea on what the solution to these systems of equations look like? Am I audible?
Yes, sir. So I since we have two variables and three equations,
Hmm.
either it will have no solution or so I think do you want us to intuitively say or solve it
Yeah,
in?
just no, intuitively, what do you think of this when you see these kind of equations? You have three equations and only two variables. Can you get a solution?
Yeah, we might get because one of them equation is might be similar to one of the equation might be a linear combination of the other two, and the remaining two might intersect. So
Right,
we might not get as
right,
well.
right, right. So there are two cases here, right? We can have a solution, we can't have a solution, right? Why we can have? If we can reduce three equations to two equations, right? What does this mean? Simple. The all the equations are not linearly independent. Basically, all the lines or planes are not essentially linearly independent. At least two of the lines or the planes are lying on the same plane or the same line, right? Then we can have a solution, right? Or it is also possible that we don't have a solution if all the three equations of line or a plane lie on the same line or on the same plane. Then we will get uh, infinite many solutions, basically, right? So, and for this case, now let's forget of everything about that. Let's start here that all the three planes or the lines are not aligning with each other, right? So let's say we have a line like this, and line like this, right? then what would you do? Fine. So that's the problem statement. Can we get a solution from here? Okay. Right. Right. So can we get a solution in these kind of cases? So the answer is no, you can't have a solution, but you can do some approximation. We can do some approximation. Fine. What kind of approximation can we make? Let's try to see this. Fine. So, okay, let me do this also. So this is a line, and then x plus 2y equals to 3. So we'll put y equals to 0, you get 3 here. Put x equals to 0, y becomes 3 by 2 here. So like this line goes like this. So yeah, this line goes like this, and the second line goes like, let put y equals to 0, x is 3 by 2, something here, x equals to 0, yeah, 1, right? So something here. So basically this kind of scenario is happening. You don't get one single point, no solution exists, right? So what to do? What can we do from here? Can we do anything from here? So we will see this. Let's try to find the solution, right? So before proceeding, Satinder was saying that you have a unique solution. Why do you believe that?
Because what I see in all the lines are concurrent lines. Because
Which
if we add what you have given the example just now, x plus y equal to 0,
Mhm,
uh, x plus 2y equal to 3, and 2x plus
mhm,
3y equal to 3.
mhm,
So if we add the line 1 and line 2, so you are
mhm.
going to get the third line. It means ki,
Okay.
the third line is passing through the intersection of the first two lines. So all three lines are concurrent.
Yeah, basically we are able to reduce from 3 questions to 2 questions, right?
Yeah, that was the answer.
Yeah. So for this case, we are getting some unique solution.
Actually,
Now the
graphically what you have drawn, actually x plus y will be on the negative side of the that side. It's 135-degree angle it will make with the origin. You have drawn in the right side, I think, 45-degree angle. What just now you have drawn the graph of this line only, I think.
so let me check. So put y 0, x 0, y is 3 by 2. Root y 0, 3 by 2. X. Yeah, right. Matlab, it will do something like this. Yeah, it will go. It will go something like this only. Yeah, fine. Okay, so yeah, this is it. Right. So so this was a simple case where we were able to reduce these 3 equations into 2 equations. Fine. Now, Shiv Kumar, you are also raising your hand. Please type your doubt.
Three is sum of equation 1 and 2. So it
Yeah.
is linearly dependent, not independent. So there is no solution, actually, unique solution. Because third equation is just a sum of 1 and 2.
Fine.
So therefore, the first two equations are linearly independent. No need to take the third equation.
Yeah, fine. Yeah, that's right. Yeah. Basically, we are reducing from 3 equations to 2 equations.
Yeah, correct.
Fine.
Yeah.
So, so this was the case where we can have a solution. So this was this case. Now, what happens if we don't have a solution? Then what will you do? Then you can't do anything. You have to take some sort of approximation. There is no other way that you can solve this, right? So basically, the second case will form this kind of graph. So you can't find a single point of intersection here. Fine. So let's try to figure out the solution to this. So for solving this kind of equation, we will deviate from the traditional way. We are looking into linear systems of equations, and we will try to now see everything as a system of matrices, right? So let's bring out this problem here. So the problem at hand is, so this was some intro, and let's start with the problem. X1 plus x2 equals to 2. X1 minus x2 equals to 0. 2x1 plus x2 equals to minus 4, right? So let's write this in matrix form. We all know how to do this, right? So it becomes 1, 1, 1 minus 1, and 2, 1. This multiplied by x1 and x2 gives us 2, 0, minus 4. Is this correct, everyone? This is 3 by 2, 2 by 1, and this is 3 by 1. So this kind of matrix multiplication is possible. Fine. This is fine. Okay. Now, yeah, this is completely possible. So everyone, do you agree with this? So till here we are fine, right? So let's start to take the approximations. So now we let's think of it as the column span of this matrix, right? We know how to solve linear equations. There are multiple ways. This is one of the ways that you can see. You can see this matrix vector product as taking linear combination of the column of the matrix, right? Linear. So let's call this matrix A, right? So linear combination of column vectors A. Fine. So let's look it like that. So I'm saying x1 multiplied by 1, 1, 2 plus x2 multiplied by 1 minus 1, 1. Can we get the vector 2, 0, minus 4? Can we go from here to here? So let's look geometrically what is happening, right? So let's try to see how it looks like. So we have this vector 1, 1, 2. So that basically goes like this. And we have the vector 1, minus 1, and 1. So x is minus 1, right? So this goes like here, right? So now the subspace basically becomes, so this is this is a plane. So these two vectors are basically spanning this plane, right? So this is a plane that is extending to infinity, right? And we have the origin here, and these two are the vectors, which are essentially the column vectors of the matrix. And the answer that we are looking for is 2, 0, minus 4. So can we take any linear combination of these two vectors? So can I do x1 into this vector plus x2 into this vector, so that can we reach 2, 0, minus 4? So yeah, if so now the problem starts here. So now we start thinking about is in the least square sense, right? Least squares. So now the least square thing comes in. Let's see what it says, right? It says, yeah, okay, fine. So for this, again, we can see if the equations are linearly independent. Yeah, the equations are linearly independent. All the three equations are there, right? So these two vectors are not aligning with each other. So this is fine. So now we can't reach, right? So let's say if the vector 2, 0, minus 4 was in the span of this space. So let's say this vector was somewhere here, right? You would have a solution, right? But that is not the case. 2, 0, minus 4 is not in the space, right? So now what you can do, you will see that this 2, 0, minus 4 will be a vector that is somewhat, so let me delete some lines from here. Yeah, so that vector will be some vector that is not in the plane of this space in this plane, but it has some, right? So this is our vector, the third vector 2 0 minus 4. So let me write this here in red. So this is the vector 2 0 minus 4, which is not lying in the plane that we are interested in which we want to find the solution. Fine. So can we take some linear combination of these two vectors to go to this? No. Why? Because this vector has a component that is not aligning, that is not present in the space itself, right? So yeah, these were the bases, let's say. Fine. So these were the bases and this is the origin. So I'm deleting up the origin right now. Fine. So now we cannot take these two bases to reach this vector because this vector has some component that is not lying in this plane. So let's draw the normal to this plane, right? Let's draw a normal to this plane. Let me take this. Let's draw some normal here. So let's use black to denote the normal to this plane. Fine. So this, let's say, okay. So let's say this is the normal vector n cap to this plane. So this is essentially perpendicular to the plane. Fine. And now let's extend this normal vector, right? So now you can see that this vector, which is, let's call it V, this vector has some components along the normal, right? So this is the component along the normal and and some component in the plane, right? So that's why you cannot take these two column vectors. So let's call this basis 1, B1, this basis 2, B2. So that's why you cannot say x1, B1 plus x2, B2 is equals to vector V, which is 2, 0, minus 4, right? You cannot get this because the vector V has some component that is not in the span of these two vectors. Now, how can, now, as I said, I want to make some approximation. I want to get some solution, which is some sort of approximation to this. Can I do that approximation? The answer is yes. And that is essentially the least square solution, which is the vector closest to this vector V. Let's call this vector V tilde. This is a vector closest to closest to vector V in the plane spanned by spanned by B1 and B2. Fine. So what will be that vector? Everyone, do you know that vector? Can anyone identify that vector for me?
A cross product of this 112 and 1 minus 2. Uh,
One.
we'll get normal vector will get the cross product and then we'll take the projection.
Right. So the projection is the answer, right? So this is the vector that lies in the plane and is closest to the vector V, right? So the question, let me put up a question. Now let's say you have a plane and this is the plane and you have some vector like this. What is the vector that lies in the plane and is closest to the vector V? That is, if you think of this, the question is, what is the vector? What is the vector V tilde such that it lies in the plane? Let's call it B1 comma B2 plane, right? Plane and is closest to V. What is the vector, right? So for this, for defining this closest property, right? How to figure out the closest thing, right? So closest is basically meaning the distance between them has to be minimum. That is, let's say we have a vector V minus V tilde. So this will be another vector. We want to ensure that the norm of this vector, L2 norm of this vector, if we are talking about the Euclidean space, the L2 norm has to be minimum, right? Minimized, right? Why I'm saying this? The question, just think of the problem that I'm posing. The problem is, what is the vector v tilde such that it lies in the plane B of B spanned by B1, B2 and is closest to V, right? So for this, we need a definition of closest. So I am giving you the definition. Definition of closest is the L2 norm, the L2 distance between the two vectors, right? So now this plane can have multiple vectors, right? So this is a vector, 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 right? This is a vector, this is also a vector, this is a vector, right? Infinite possible vectors in this plane. The question is, which one of them is closest to V, right? So are you getting the idea how I'm posing this problem? Everyone, is the problem clear to you? Right. So now the question is, which is the vector V2 such that V minus V tilde L2 norm is minimized? The solution to this is essentially the least squares problem. This is the least squares problem. And geometrically, you all know the answer, right? This is the projection of this vector on the plane, right? This is its component along the plane. Basically, everyone knows this answer because we have already done these kind of problems. So now this is the point. This is the vector v tilde. This is the answer that we are thinking of, right? So the answer is projection of, yeah, orthogonal projection, right? Projection can be of multiple ways, right? Orthogonal projection of V onto the space spanned by B1 comma B2. Now, how to find the orthogonal projection? You all know, right? We have solved this problem. Anyone, do you have any doubts in this? No one has any doubt. Shiv Kumar, you have raised your hand. What is the doubt?
The doubt I got was this vector 204, we have to take two components, one along that 112, another along 1 minus 1, and whichever gives the least is considered as the um, what do you call the solution or the projection of the
Yeah,
vector
this
on
is the
it.
least. This will be the least square solution to this problem.
Uh-huh.
So that this will give you the vector which is in the plane and closest to the vector V2. V. Yeah. Fine.
So the vector v, which is on the right hand side, that is 20 minus 4,
Yeah.
that projection you're taking along x1 and x2.
Taking along the vector space spanned by 1, 1, 2, and 1 minus 1, 1.
Oh, okay.
That will give you x1 and x2. X1 and x2 is scalar, right? X1 and x2 are simply scalars.
Okay. Yeah, things
Right?
clear now. Yeah.
Yeah. Now, how to get to this? Basically, one thing just I need to is emphasize that for closest, I am not talking about the exact L2 norm. I'm basically dealing with the L2 squared, basically squared of the L2 norm of the difference vector, right? This is essentially the distance between them. And when you minimize, so basically you take the argument of norm of V minus V tilde squared with respect to V tilde, you get the answer. And it will be essentially, the answer would be AX, the answer will be A transpose A X is equals to A transpose whatever on B, right? So this will be the answer. How to get to the answer? I hope you have seen the video lectures, or you can figure this out on own. Just simply write the equation for this and try to minimize this equation, and you will see the answer, right? Anyone, do you have any doubts in this? With so Rohan, can you explain your doubt?
No, sir, no doubt. I just wanted to say that got you up till now.
Yeah, it is covered in the lecture, right?
Yeah, yes, sir. Yeah.
Fine, that's great. So this is also known as pseudo inverse, and multiple names are given to this term, right? And now the thing is, why it is pseudo inverse? Again, because you are able to try solve the problem ax equals to b, where a is not square, right? Non-square matrix. So that's why it's also known as a pseudo inverse, because you are essentially trying to do some sort of inverse operation on a to get x. But yeah, let's not get into that. But this is something known, well known. Now, if you put the values of a and b in this equation, you can get the solution of matrix vector x, right? So, thing to note here is a transpose a will be a square matrix and invertible square matrix. So you can simply get the solution as a transpose a whole inverse a transpose b. So this is the answer to this problem. Now I'm not going to solve this equation for you. You can do this on your own. This is just how to get to the answer. Just put in the value of matrix A and B and the vector B in this and you will get the answer. Fine. So I think Rohan has a solution also. Answer will be -1 comma 0, right? So yeah, this is how we do this. This is very very useful result. This is a very useful problem. This is used in a lot of places. Even the newer machine learning algorithms also basically rely on this only. So they use this and call it different names. But this is the core that is being used. So how to build from this? What is the application of this kind of algorithm, this kind of problem? The problem is, let's say in the space, you have multiple points, right? Sampled in the space, right? The question is, let's say we are considering only 2D case. These are multiple points spanned in the space. The question is, uh, can you find, yeah, can you find a line that passes through this these set of points, right? So the use case of least squares is basically this is what least squares looks like. You want to find a line that passes through all the points. And since these points are not in a line, you can't find a single line that satisfies this criteria. But using least squares, you can find a line that approximately is closest to all of these points. So this is a useful algorithm that is used in machine learning. But yeah, so this is useful in this kind of problems, right? So because now there are multiple lines, right? This is a line, 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 this is a line. The question is, which is the line which passes through all the points? You can't get a line because these points are basically not in a line, right? This is a non-linear curve, but you can always approximate an approximate curve that is closest to all the points. And then now let's say you want to approximate a value at this point. You don't know the data actually, you know only this part of the data, but using this line, you can predict that what will be the value corresponding to this X value, right? Using this information. Fine. So let's say you get this least squares fit, right? This is a solution. Now using this, you can always make approximations for new data points. So for this X, the Y value will be this. For example, the X-axis represents the area and Y-axis represents the price of houses in that area. Then this is the data of existing houses, right? From here, you can always approximate, like let's say for we have um, let's say we have this X value. We want to find the price of houses in this region, right? So simply go to this line where there is no data is present, and simply you can predict the house price for that region, even without knowing any information on that, just by the data that you have on the existing houses, right? So this is the use case of least squares. You will find them in your advanced classes, but yeah. So this was all about least squares. I hope I have covered everything. If you have any doubts, you can ask me. Fine, I think everyone is clear. So let's move on to the next question. Right. If A is a 3 by 3 matrix with real entries with column vectors, A1, A2, A3, then A, which of the option is true? A into A is equals to identity. A is orthogonal if and if only if. Let's everyone. I hope the problems were with you. Let's try to get to the answer quickly. So for option one, A into A is identity. Is it true for all the vectors, all the matrices? So basically, let's say you have a matrix A, basically A1, A2, and A3. And what I'm saying is, it's a 3 by 3 matrix. I'm saying is A into A is identity. Is this true? Anyone? This is not true
No.
always, right? This is not always true, right? So this is a wrong option. Option B, A is orthogonal if and only if AI dot AJ equals to 0 for I not equals to J. Let's look into this. So what is the definition of orthogonal matrices? So the definition of orthogonal matrix is basically this only. Option B is the definition for orthogonal matrix. So basically the column vectors have to be orthogonal with each other, or the row vectors have to be orthogonal with each other. Any case, it will be an orthogonal matrix. So option B is correct. Option C says
B
A
is false, no?
transpose. Yeah.
Uh, B is false, no? Because it give like one of them, if one of them is becomes zero column, then also it will
Okay. Yeah.
happen. So along with orthogonal columns, we need orthonormality, like normality of.
Yeah. 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 Right. You are right.
So we have a suitable
Hmm.
option in D. So D is basically combination of B plus the required thing, which is not provided in B.
Okay. Yeah. The question is then. Yeah. Right. You are right. This is not orthogonal. It has to be orthonormal here. Orthonormal. Basically, orthonormal matrices are matrices where this is property is happening. Right.
Say D is orthogonal actually, no? Like because A is
No,
square matrix.
orthogonality. It's again, it's quite basically a definition based problem, right? What is the definition of orthogonal and what is the definition of orthonormal? So essentially, they are considered mostly equal, but I would like to call it orthonormal because of the normality constraint that the AI dot AI has to be one.
Yes, actually, so that's a very debatable thing. So
Hmm,
Gilbertstein in his book
hmm,
also mentioned that
hmm,
orthogonal matrix by the name, it only says that the columns might be looking orthogonal. But in reality, the
hmm.
standard convention taken is orthonormality plus a square matrix thing. So if a square matrix is orthonormal, then it is called orthogonal. So yeah, there is a little bit debate. You're right, actually,
Yeah,
about the definition.
so I don't want to get into that debate, so I am just ignoring this orthogonal term altogether. So this is not here, right? Fine. So A is orthonormal if and only if it A I dot A. Right, you are right. So option B, this is again, yeah, you're right. If any one of the vectors becomes zero, then this won't be an orthogonal. Option C, why this option C is wrong? Because for orthonormal matrices, A transpose A is equals to identity. So this is not true always. So option C is not true always. Not true for orthonormal matrices. Fine. So option C is wrong. Here I can say AI or AJ can be zero, right? And yeah, good. This is not always
Sir,
true. Yeah.
uh, sir, can you just explain why you wrote not true for orthonormal matrices besides C?
So basically, when you look into the properties of orthonormal matrices, you will see that A inverse is essentially A transpose. Sorry, A inverse is essentially A transpose for orthonormal matrices. So this is a property of orthonormal matrices. So now when you do A into A inverse, which is A into A transpose, you get identity, right? Now, since A inverse is transpose and inverse A inverse is A transpose, right?
Okay, okay,
Then
right, right.
A
Yes,
inverse
yes, yes.
into A will be identity, which is A transpose A. will be an identity matrix.
Right, Sam. My bad. Yeah, right.
Fine. You want me to prove this also, this property? This is very simple.
No, sir. It's
So
fine. Like, I misinterpreted it actually. That's why.
yeah.
But in the question, it has been not mentioned for this one, no? Orthonormal. In the question, it has been not asked. I think always it will be not true. A transpose into A will not be equal to I always. Because in the question, it has been not asked for the orthonormal.
Yeah,
No,
Satvinder, I
no.
also got the same doubt. Like that's why I asked that. So he's saying that for
Uh-huh.
orthonormal matrices,
Then that
it
I've
is I.
understood. Sir has explained. But I think it will be false because it will be always not true. Just we have to consider that.
No,
Uh,
no.
uh,
Basically, A transpose A will be equals to identity for orthonormal matrices. So
Actually, in the question, it has been not mentioned. No, in the question, it has been not asked
no,
for the
no. The
orthonormal.
question is saying
It
for
is a general
any
case.
matrix. The question is saying any matrix, right? So you have a set of
Uh,
matrices, right? Let's say set of
mhm.
matrices of dimensionality 3 by 3, right? This is a set of matrices. In that set, you get a set of orthonormal matrices, right?
Same thing, same thing. Means for the
Matrices
orthonormal,
or
this condition will be
and for this A into A transpose equals to A transpose into A, which is identity. For other cases, it will not be. A transpose A will not be identity. But there is a set where you will get this. So that's what I'm saying. Is this clear? Satyender, is this clear?
That option B is
Yeah.
like dot product being zero, no?
Yeah.
AI dot AJ equals zero for I not equal to J
Yeah.
is dot product. So
Yeah.
that angle becomes pi by 2.
Not necessarily. A, I, or AJ can be zero vectors themselves. Also. That is also a case. So basically, if AI is basically, let's say 0, 0, 0, then you choose any vector, you will get AI dot any vector, you will get 0, right? Either it is orthogonal or not.
Oh, so that if and only if it can be has to be removed.
Mm. No, there has to be some condition here that AI is non-zero, and AJ is non-zero. If you add this condition, it is true.
Thanks.
Yeah. Anyone else? Do you have any doubt? Satyendra, you have any doubt?
for the fourth option,
Yeah.
uh, orthonormal. That I'm understanding A dot J will be 0.
Hmm.
And then it is written one otherwise. So what is the meaning of one otherwise? This I'm not
Yeah.
understanding.
Yeah, yeah. So look at this kind of notion is used in maths whenever you want to put if and else conditions. Like if I is not equals, so think of it like this. If I is not equals to j, I is not equals to j, then ai dot aj equals to 0. Else, let me move this. Oh, sorry.
Else means if I equals J.
Else ai dot a j is equals to 1. So think of it like this. Now it's clear.
Uh, I
What?
AI dot AI, no?
Uh,
When I is equal to J.
so this essentially means I equals to j, so it will become ai
Uh,
dot ai. But
it means ki, the vectors are unit, like the column vectors are unit vector.
so
For
that's why I'm
orthonormal,
using this. Yeah.
Mhm.
So that's why I'm using this ortho unit normal term here. Fine. Any other doubt? So let's move on to the next topic, next problem. Suppose u, v, and w are three vectors in the same directions, then the projection of u, v, and w in the direction of u is. So let's see. So we have vector u, vector v, and vector w, and it's saying in the same direction, right? So u, v, w in the same direction. Then projection of u, v, and w in the direction of u. Acha, you want to take the projection of v and w in the direction of u, right? So which will be essentially meaning. So let's do this. Very simple. Projection of v on u, right? V dot u cap in the direction of u cap, right? Where u cap is essentially u by norm of L2 norm of u, right? This is u cap, right? Fine. And projection of w on u is essentially w dot u cap dot u cap, right? It's a very simple thing to see. Basically, let's see. V dot u cap is essentially norm of v into norm of u cap, right? Into cosine of angle between them, and all three are in the same direction. So cosine of 0, which will be 1. So this is essentially v into u cap in the direction of u cap, right? So now u cap is basically pointing in the direction of v, and the norm of u cap is essentially 1. Norm of u cap is 1. So this becomes norm of v in the direction of u cap. Now, since u cap is in direction of the v itself, so it becomes norm of v in the direction of v cap. Now, norm of v into v cap is essentially norm of v into vector v divided by norm of vector v, which is essentially vector v. So projection of v on u is essentially v. This same proof, same way you can see that this will be w, and the option D is correct. This is not a zero vector, not possible. So second, so option B is already wrong. Are using vectors along the direction of, I don't know what this means. The option D is correct, right? Yeah, Rohan, you are right. You can get to this answer geometrically also, because what is the projection of u in the direction? That is the same thing, what I've done here, right? Anyone, do you have any doubts in this? Rohan, do you have doubt in this, or this is fine?
No, sir, this is fine. So yeah.
Fine. Let's move on to the next question. Last question. So let A be a real matrix, which of the following is true?
For question number 8, what is the correct answer?
Option D, V, and W themselves.
Option D. Okay, thank you.
Yeah.
Sir, before you move on to the last question, before moving on, can you just give a recap of what is a keyword decomposition? Like, what is the condition? Suppose a matrix you are decomposing into keyword. So, what is the essential condition needs to be imposed on Q and R?
Okay, so wait a minute.
So, sir has covered this actually in his lectures. But the thing is, in a different book, which is also very standard. So, I found that like their definition is little bit different. Not different. It is a quite a general kind of a thing. So that's why I said that last question I have a doubt, like before, because I'm not sure about the definition of keyword decomposition.
Okay, so yeah, so let me basically, there are multiple books and they all use some different conventions, but in the end, if you look at the maths, that is true for the conditions imposed for proving that thing, that any kind of theorem there, right? So that's why it becomes somewhat confusing sometimes. So let me
Yes.
tell you what I know. Yeah. So Basically, I will follow the same thing that is told in the lecture itself. So I can't. So I'm trying to project that notes here, so I don't need to do anything on my own. So let me see.
Sure, sir.
Week 7, right? It was lecture 35, right? Yeah, this is the lecture. Okay, 34 is also there.
How you went quickly to this lecture 35?
This is the lecture, the topic, right? Covered in the lecture itself.
That is theory lecture.
Yeah, theory lecture, right? Yeah. So basically, this is not useful. This is not useful. Kramer's rule. Okay. So this was it, right? This was anything extra from here? I'm just trying to figure out.
Let me check the I'm not sure about in which 34 or 35 in which the covered keyword.
Okay, so I have the idea for the algorithm. So let me cover it here. I got the idea what they're trying to say. Right. So
Right.
let's say you have some sort of matrix M. Let's say I have a matrix M with column elements as M1, M2. Let's talk about 3D matrices only, 3 by 3 matrices, right? So M1, M2, and M3 are all three-dimensional vectors, belongs to R3, right? Now let's think, right? Let's think geometrically. Now let's say I have a vector, this vector, and let's call it the vector M1, right? This can be any vector. I'm choosing the vector M1 in this space and I'm drawing it. Everyone,
Right.
can you figure this out? This is the vector M1, right?
Yes, sir.
Fine. Now what you can do, you can define a space which is perpendicular to this vector M1, which will be this space, right? This is the space which is perpendicular to the vector M1. Everyone, do you agree with this?
Yeah.
This is the vector perpendicular to M1, right? Now, let's say we have a vector M2, which is another vector that can be in the space, right? So let's say we have this another vector M2, right? Now, can you say this that M1, M2 can be written as some alpha times M1 plus beta times the plane. So basically beta times some basis, basically what do you call the span of the plane, some vector, some beta times, let me write it like this, beta times some vector v, where v is in the plane that for which m1 is a no is along the normal, right? Is along the normal. Fine, along the normal. Do you agree with this, everyone?
Yes.
Fine, everyone? Right. Now, what I'm saying is, let's forget about M2. Let's figure out some another vector. Let's take V from here, right? So I can always find of V. We know M2. So M2 is known, right? M1 is known. And we can always find the projection of M2 on M1, which is very simple problem. So you can always figure out BV, right? Beta V, right? Beta will be M2 minus alpha M1, and then V will be M2 minus alpha M1 divided by beta, where alpha comma beta can be found, can be figured out using the techniques that we have seen, right? Everyone, do you agree with this? Do you have a problem with this? Anyone? I don't need to solve this, right? Because it has already been covered in the lecture, right? Now, what can you say about M1 and V? M1 comma V. Are they orthogonal? I'm not using the word orthonormal. I'm saying are they orthogonal? right? Great, right? So you can say m1 dot v equals to 0, right? So now let's take these two vectors, m1 and then orthogonal vector v here, and now draw think of the space that is orthogonal to these two vectors. Now in the 3D space, you only get one direction which is perpendicular to these two vectors, that is perpendicular to both of these vectors, right? Which is this. So this is perpendicular to v also, and this is perpendicular to m also, right? So now what will be that vector? Now let me yeah, right. Now I can write m3. My m3 will be some vector. Let me draw m3 again here. So let's use red for m3. So m3 will be vector that, let's say, looks like this, right? And you all can say that m3 has some components. Let's say a m1 plus b into v plus c into something. Let's call another vector v2, right? Let's call another vector v2. Now again here, what you can say that, what is the v2? V2 is vector along the normal to plane spanned by m1 and v, right? So this is the vector. Now from here I can figure out v2 is equals to m3 minus am1 minus bv divided by c, and a, b, c can be figured out easily. You all know this, how to figure this out, basically, right? Simply take the projections along them and you will get the answer. So now if you do this, you get three set of vectors. One is m1, another one is v. Let's call it v1, right? Let's call it v1 everywhere. Let's replace it. This is v1, right? So m1, v1 and v2, all three are orthogonal. And if you put the matrix form, you get m1, v1 and v2. So if all three are orthogonal, this will be an orthogonal matrix, right? Right, everyone?
Sir, by the exact definition, if it is square, then it will be orthogonal. If it is not,
Since we are dealing with in the 3D space, right? We are only
okay,
considering three vectors, right?
we'll see.
Yeah. So everything is in 3D space. So let's not get beyond that. So it's a 3 by 3 space. Okay. So now this is an orthogonal matrix, right? Then your M can be written as Q into R. So let's see what is QR here. So basically, everyone, do you understand this process, right? What I was doing, very easy, very simple steps that I was following using the ideas that you have seen already. Now from here, I am building a pattern here. So let's call this orthogonal matrix Q, right? Q is a 3 cross 3 orthogonal matrix. Now you will see that you have a vector M1, you have a vector M2, and you have a vector M3. And let's write this orthogonal matrix m1, v1, v2, right? Multiplied by something. What is that something? So this is matrix m, this is q, right? Now you all know that this product, let's say this, let's call this for now, let's say this is R matrix, and I'm just I'm not defined any properties of the R matrix. R is any general matrix of dimension 3 by 3. Right. So we all know that this matrix vector product can be matrix product can be written as QR1, right? QR2, QR3, right? So this is your basically I'm saying M is equals to this, right? Now let's check the vectors. All the vectors have to be the same. I'm saying a vector matrix 1 is equals to matrix 2, then all the column vectors have to be equal, right? So M1 is equals to Q into R1, right? So M1 is essentially equals to M1 V1, V2 into some vector R1. Now, anyone, can you tell me what this vector R1 will look like from here, from this simple idea? 1, 0, 0, right? Very simple, straightforward. Now, again, I'm saying M2 is essentially equals to M1, V1, V2 into R2. This is a vector R2. Now, we had seen this relation M2 is equals to alpha M1 plus beta V1, right? So we also saw that M2 equals to alpha M1 plus beta V1. Now, using this information, anyone, can you tell me what this vector R2 will look like?
0, 1, 0.
No, it will look like alpha and beta, right? Alpha, beta, 0. Alpha, beta, and 0. Is this
Oh,
correct, everyone? Do you agree with me on this? And similarly, M3 will be M1, V1, V2, right? And again, M3, we know that A M1 plus B V1 plus C V2. So it will become A, B, and C. This will be your R3. Now let's put everything as it was in the beginning. So I said M is equals to some matrix Q into some matrix R whose row elements are 1, 0, 0, alpha, beta, 0, A, B, C. This is the R matrix. Anyone, can you tell me the property of this matrix just by looking at the entries of this matrix?
Upper triangular
oh,
matrix.
oh.
Great. So what we have done here, we have decomposed the matrix into an orthogonal matrix, a product of an orthogonal matrix, and an upper triangular matrix, Euler matrix. And now this decomposition is essentially known as QR decomposition. This is the basic idea. Now you can choose any convention you want, right? Someone will say all the vectors have to be unit vectors. Someone will say like all the vectors in the matrix Q have to be unit vectors. That is, Q has to be orthonormal matrix, right? Then R will scale up. So if it's like this, you say A into B equals to 10. So this can be 2 into 5. This can be 10 into 1. This can be 2.5 into 4, right? So you just have to see that there are multiple ways of saying this. But the inherent idea is you can always write a matrix as a product of orthogonal matrix Q and an upper triangular matrix R. The thing is, if the question is, can you write all the matrices like this? Yes, you can always write this. You will never see a matrix that you can't write like this because we took no assumptions here. Yeah, there is one case like in which M1, either of M1, M2 or M3 might be 0. In that case, again, you can set R1 and R2 and R3 to be 0, and you will again get a decomposition. So QR decomposition always exists, right? For real matrices at least. So now does this clear your doubts, Rohan? Now all the books or wherever whatever literature you will review, you will find there some convention, some constraint put on the properties of the matrices or the vectors involved in this decomposition to giving some sort of decomposition. But this is the core idea, what is being done here. Now, Rohan, is this clear?
Right, sir. Sir, your approach is very clear to me. So
Hmm.
most of the books, the dilemma that I was having is they are saying
Hmm.
two things. One is
Hmm.
uh, full QR decomposition, and one is reduced or thin QR decomposition. So and that is
That's right.
coming out of like if one of these vectors M1, M2,
Hmm.
M3, if one of them is linearly dependent on the other two.
Hmm.
Suppose these three are not linearly independent.
Yeah,
So
yeah, yeah.
you so the problem arising is you can't have a queue, like you can't have a orthogonal kind of a thing. I was
Yeah.
thinking it in this way.
Hmm. That is fine, right? Because let's say you have this kind of matrix 1, 0, 0, 0, 1, 0, 0, 1, 0. Let's say I'm writing this matrix, right?
Or
You
maybe
can
one
write
one
it
zero, the
as,
last column, sum of first
okay,
two columns. Yeah.
okay, you can put 1 here, right? 1, 1, 0, right? So now, how can I write this? I can write it as 1, 0, 0, 0, 1, 0, 0, 0, 1 multiplied by
Okay.
So let's say 1 0 0, 0 1 0, and 1 1 0. Is this correct? Right? This is upper triangular. Yes. This is orthogonal. Yes. So you get a QR decomposition, right?
Okay.
Fine.
Yes, sir. So keyword decomposition always exists, right? For any matrix.
Yeah, yeah. For any real matrix with real entries.
Okay, so we have solved one part of it when it is square. So when it is square, we can say that it is always possible to do keyword decomposition. What about if it is rectangular? Let's say 3 by 5 or 5 by 3.
Yeah, this kind of measure is right. So was this covered in the lectures?
Sir has only given the 3 by 3 case, but
Ah.
the question that you have given, it doesn't mention 3 by 3 or a square matrix. So it in general says whether keyword decomposition is always possible or not.
So let's retrace the path, right? How did we get to the QR decomposition? We started with some vector and started proceeding, right? So now let's say
Right.
instead of M1, M2, and M3, I had only M1 and M2. Then what would you do? So
Yeah,
in that case, you will choose M1, right?
so it is 3 by
And
2,
you have
right? It's a tall matrix.
it's a tall matrix. No, it's a rectangle. No, 3 by 2. It's a rectangle, wide matrix.
Tall matrix, you know, not a vertical one. Horizontal would be 3 cross 5.
Yeah. So you choose M1 here, and then you can choose M2 here, right? So you can write it as M1, and then V1 was right. It was V1, right? V1 multiplied by your R has to be 1 0 0, and then V1 was alpha beta 0, right? And 0 0 0. So now this is not a full Q matrix, right? This is a reduced Q matrix.
So here
And
actually the
this
doubt arises.
cross.
So this book that I was referring, they are making it again a 3 by 3 with the same procedure. Like they are saying you can make it 3 by 3. Let's take the last column, one orthonormal basis from R3, and you'll adjust it in the R's part. Sir, is it fine if I post a snap in the message and you can look at it once?
Yeah, you can post the snap, but what I'm saying is, you can post the snap, but you look at this, right? So now, if you think of it like this, you keep posting the snap. I'm just explaining it here.
Yes, sir. Yeah.
So now let's say I'm saying it like this: alpha, beta, 0, right? And now this is a 3 cross 2 matrix, right? Now, is this matrix product possible? Is this allowed?
No.
Right? I think your photo is not visible here. There is some issue with it, but let me just clear this part, right? So you cannot say, right? You cannot think of anything. You can't do this product, right? You can't say that this is QR. Why? Because this is a 3 cross 2 matrix. This is also a 3 cross 2 matrix. You can't do this, right?
Right.
Now you also know that the third matrix is a 0 matrix.
Okay.
Sorry, the third vector was a 0
Third
vector,
column.
right? Third column, right? You can always insert a 0 vector here as a third column.
Maybe not 0.
And you can
we take a orthogonal vector, which is orthogonal to both M1 and V1,
right.
which is not present
That
here.
also works. Yeah, that also works. Yeah. So you can take something orthogonal, which is V2, let's say, and then you can put 0 here, and then it becomes a full QR decomposition.
Right. Yeah. Sir, actually, I have a little bit of doubt still. From can you try copy this, or like can you download it and paste it there so that I ask? It will be easier for me to ask you then. Is it possible for you to copy or download this image? I've
This
sent
is
in
saying,
chat.
now I can see the image. Yeah.
Okay.
What's the chat box? Yeah, this is the chat box, right? Is this visible?
Right. Yeah. And so it is particularly taken from this book, Golub and Van Loon. So
okay,
and they are saying keyword factorization to be this, and which you did actually. So one doubt you have already adjusted, that even if we are not having the square kind of thing, you are making the third column or the fourth column as many columns as needed. You are bringing that into picture. That one doubt is satisfied. The second doubt is like they are saying, can you go back to that image once more?
Yeah.
Yeah.
Hmm.
Yeah. So they are saying that upper triangular matrix R, which is of size m by n. And when I looked it up in the internet, upper triangular, how can it be for rectangular matrices as well? Or will
No,
it
no,
look
this is
something
with this.
similar to?
This is defined, right? So let's think of this. Let's go to back to this problem and this example itself, right? So I am saying the last column I have putting it 0 here, right? For the sake of completeness,
Right.
it has to be square matrix, right?
Yeah, yeah.
Now what if I drop this? Now let's not take this R, let's take R1, which looks like this: 1 0 0 alpha 1 0. Sorry, 1 0 0 alpha 1 0, and this is a 3 cross 2 matrix, right?
Right.
Is this fine?
Yes.
And let's take our Q matrix as M1, V1, V2, right?
Yes, sir. Yeah.
Fine. So now
Yeah.
this is a 3 by 3 matrix. This is a 3 by 2 matrix. The matrix product is possible. Fine.
Yeah.
Now
But can we
what I'm
say R is
saying,
upper triangular?
yeah, this is upper triangular. This is well defined, right? So
Okay.
even for rectangular matrices also you can say this. So what the only thing you have to pay attention is for this matrix, the diagonal will be this one, right?
Okay.
So basically diagonal is always there. So the definition of a diagonal element is I comma I. That's it. So this
Okay.
is elements 1 comma 1. This is element 2 comma 2. So below this elements you are getting zeros. So it's a pattern. That's it. Yeah.
Oh, okay. Okay. Now got it. Now fully understood. Yeah.
So these kind of factorizations, everything, anywhere you are reading, anywhere, basically there are multiple ways to represent these things, write different things. Just pay attention to what is the constraint given there. That's it.
Okay,
So
but there
let's.
should be a convention, right? That everyone is accepting. Otherwise, there will be a lot of dilemma when someone is saying keyword decomposition. So there must be one convention.
That's why whenever we put something formal, that let's say I'm writing a book or I'm writing a paper, I will formally explain that I'm talking about this specific reduced QR method or the full QR method. And if the method itself is ambiguous, the name is ambiguous, then I will explain what that method says, what is the constraint on the matrices, and what the result looks like.
Okay, okay.
So formally, there is a convention, and whenever you are using that convention, that has not, it must not be ambiguous. But if it is ambiguous, then you will give all the statement involved in that.
Okay, sir, got you. Yeah.
So let's get to the last question. Let A be a real matrix, then which of the following is true? The matrix A as always, yeah, that's true, right? Option A is true. We already saw this. We can write for this for any kind of matrix. The matrix A has PR only when the columns are A. No, that's wrong. QR decomposition is possible if A is a square with full rank. No, I mean, this is possible, but not only if, right? QR decomposition is possible only if A is a tall matrix. This is completely wrong. QR decomposition is possible only if A is a wide matrix. No, this is also wrong. So QR decomposition is true for exists for all kind of matrices.
Yes, sir.
And this
The
is
only
very.
doubt is like some people are saying the dilemma is between A and B. So the full QR and reduced QR or thin QR. So you're right,
Uh,
actually.
it's about the convention, right?
Yes, sir.
Hmm. So you can let's think of it like this. I'm writing a matrix which is of dimensions 3 by 2. It contains two columns M1 and M2. I can always write it as a matrix that looks 3 by 3, M1, M2, and zeros here. You add as many zeros as you want and you call it a square matrix again. Fine. It's a way of representing things, and SVD basically reduce SVD essentially uses this information that the bottom half of the R matrix has will be. So this is, let's say if it's a rectangular matrix that looks like this, right? So this is M cross N with M cross N, sorry, M cross N with M greater than N. right? It's a rectangular matrix. You will see that the upper triangular diagonal will look like this, and this is upper triangular matrix. So these all entries are zero, right? So either
Yes,
you
sir.
write this entire matrix or you take up the first half, the upper part, right? This small part, and you take this part and put it like this. Then this is a reduced R. And if you write it in this kind of reduced Q and reduced R form, then you will get reduced SVD decomposition. That's it. Is this
Right, sir.
fine?
Yes, sir.
And
So in
why is
SBIT, okay, yes, sir. Go on.
yeah.
Sorry.
And why it is useful is because let's say you are doing some calculation of QR decomposition. Initially, when I started the LU decomposition itself, I told you that why we are using this because there are various use cases. Like for example, doing faster numerical computations, linear solves, or other things, right? So now why we want to use the reduced QR? It takes less space. Let's say if you want to enter a matrix of dimensions 10,000 cross 100 into the system, and you know that only 100 cross 100 can represent the entire matrix. So let's say this is an upper triangular matrix R, right? This is upper triangular and the
Yes.
matrix dimensionality is 10,000 cross 100. You know that all the entries below the column 100 will be zero. So you don't need to use store R. You can store R cap. That is 100 cross 100, right? And you are
Right.
saving a lot of space, right?
Yes, sir.
Is this clear?
So
So these
one
are the
follow-up question. Yeah.
uh,
Sorry. Go on. I'll ask it later.
so
Yeah.
these are the applications why we can go into this reduced forms and other things. That's it.
Okay, sir. Nice. Sir,
Mm,
so for LU decomposition, we have seen this that
mm,
we did LU decomposition because it helped us in forward substitution, backward substitution, and we
mm.
solved the system of linear equations.
Yeah,
So, what is the use case of QR decomposition? Why do we do that in first place?
that is also interesting. You can also use it for solving, right? Let's see. You are doing ax equals to b and square. Let's deal with square matrices. So a is q, rx equals to b. You know that the inverse of q is q transpose. So you say q transpose q rx equals to q transpose b.
Okay.
Now this is identity matrix. So you get rx equals to q transpose b. Now here from here you can say x equals to r inverse q transpose b. Given r is a upper triangular, the inverse operation can be fast.
Yeah, right. So
Sorry,
it
sorry.
will
You
be,
don't need to. There's a
yeah,
back
actually,
substitution, straightforward back substitution here.
right.
You simply do back substitution. So yeah, it is
Oh, wow,
use case
that's
the
nice.
most substitution. That's a very basic use case.
Nice, sir. Yeah, got you.
Fine,
Yeah, yes, sir.
great. Fine. So let's end this session for today. There are other problems for week 8 also. I will just solve those problems in the next session itself. So let me update 8 here.
Question number 11, option E, I want to write down.
Yeah.
Question number 11, option E.
Question 11. Yeah. Option.
E is
Yeah.
QR decomposition.
QR decomposition is possible only if A is a wide matrix with rank n, where n is the number of columns of A. We have already seen that the QR decomposition is always possible for any kind of matrix if it's a real contain real elements. So
Sir, this
this
kind of
option is
matrix is not possible,
not
no?
wrong. No, why this kind of matrix is not possible?
So they are saying that A is wide matrix. So let's take A is 5 by 7, or let's take
Yeah,
5
yeah,
by,
yeah, yeah. So what's the
and
problem in this
they are
matrix?
saying, that rank is 7.
Rank is
7 they are saying. Rank is
no,
n.
no, no.
So rank is number of columns.
N has to be number of rows. Yeah, the question is wrong. Let me put it like this: the number of rows of A,
Now it makes sense.
because it's a now it's correct. Fine.
Yeah.
Thanks. Okay. So is the doubt cleared?
Thank you.
Yeah. So
Excuse me, sir.
yeah, what's the doubt?
I have a doubt, a small doubt. Like if a matrix what we are taking,
Hmm. So
if A comes out to be orthonormal,
hmm.
uh, if A matrix is normal, then a
Hmm.
QR decomposition is possible.
Yeah, that also is possible.
Because we can't get the projection of one of the vector on the other because it is already perpendicular.
So that's not a problem, right? So R will be identity in that case,
Uh, okay, got it.
right?
So identity matrix that will be upper triangular always. Tick.
Yeah.
Okay.
Okay, fine. Any other doubt?
Sir, this PDF is finished. In the next lecture, I think you'll be taking another PDF. So before that,
Yeah.
can you give it to us so that we can try it ourselves first, and then we can see your approach as well. So it will help us.
Which PDF you're talking about?
So this one is done, right? So in the next
Yeah.
class, the PDF you'll be
Hmm.
starting with. If we
Hmm.
get that PDF 1 or 2 days earlier, then we'll get to
Hmm.
try it on our own as well. And then we can. Yeah. So is it
Okay,
possible?
fine. I will. Yeah, I will try to share it if it's finished before the session.
Okay, sir. Yeah.
Hmm? Yeah.
Yes, sir.
Okay. Fine. So everything. So let's end this session. Let's meet next week, right? Thank you all.
Thank you, sir. Sir, I think Shiv Kumar sir wants to say something. He has raised his hand.
Yeah, Shiv Kumar.